Hi everyone, my name is Stephen Lawrence and today I will be presenting the paper Solar, Deep Structured Representations for Model-Based Reinforcement Learning. This paper was published in 2019 in the International Conference of Machine Learning. The authors are Marvin Zhang, Sharad Vikram, Laura Smith, Peter Abil, Matthew Johnson, and Sergey Levine. Sergey Levine is well known for his work with reinforcement learning and robotics from UC Berkeley. We'll begin by looking at a quick introduction highlighting the importance of this paper. We know RL has established itself in simulation by surpassing human abilities in games such as Atari games, chess, Go. However, scaling RL to real-world applications has been challenging. There are some proposed scaling solutions using world/global model-based reinforcement learning, unsupervised meta-learning, and representation learning. So what is the problem when scaling RL to the real world? Well, in simulation, these agents have access to low-level state information. This is an unrealistic expectation when scaling to real-world scenarios. So the question is, how do we solve partially observable MDPs from just complex RGB images only? This paper introduces Solar, and that is a solution for such a scenario. So what is the proposed solution? This paper introduces a framework they call Solar. Solar stands for Stochastic Optimal Control with Latent Representations. This allows for the policies to directly come from high-dimensional image observations only, eliminating the need for that low-level state information agents get in simulation. How does it do this? It uses a model-based reinforcement learning agent. It builds a global model through environment interaction. It performs representation learning to extract features from the environment, uses its learned representation and global model to make inferences to explain local model observations. It uses LQR-FLM policy optimization to update the policy. We'll talk more about this in upcoming slides. Before we dive in though, we'll look at some background information to help better understand the proposed framework. To begin, we'll look at model-based reinforcement learning, some of its advantages and disadvantages. Model-free agents can outperform model-based agents, but they typically require 2 to 3 times more magnitude of samples. This makes model-based reinforcement learning significantly more efficient than model-free. A disadvantage, though, is that they are outperformed by model-free agents, and something called model biasing can occur. This is when an imperfect model is formed, and it can result in poor real-world performance. If you look at the graph on the right, we can see Solar, within 1400 episodes, outbeats the other model-based frameworks, such as RCE, VAE ablation, MPC baseline. The only one that outperforms Solar is PPO, but as we can see, it took almost 40,000 episodes to perform this optimally. But within only 1400 episodes, Solar is able to converge close to PPO, enough to complete the task. I did have 2 nice videos to show with the class on modeling bias, but they do not appear to play during the recording. But essentially, PPO on the right, this car starts in the bottom right corner and has to travel to the point in the top left corner here. So the goal is just to have the car travel up the chart and get to the goal. And what we would have seen is PPO would have had a very smooth trajectory, whereas Solar had a lot of jittery movements, and this is caused from that modeling bias. But the upside is Solar was able to learn to go from the start to the goal a lot more efficiently than PPO had to. An essential component for the Solar framework is representation learning. Solar uses representation learning to automatically detect features from raw input to build a global model. This allows the agent to learn and use features to complete tasks, and Solar will optimize its learned latent representation to infer local models for policy optimization. The last topic to discuss for background is linear-quadratic regulator with fitted linear models. So what is LQR? It is a popular solution for solving or for optimizing LQ problems in control theory. LQR has had success in a number of control domains, including learning new tasks on real robotic systems. The L means the system dynamics are described by a set of linear differential equations, and the Q is for a quadratic function that describes the cost. LQR requires the cost function parameters to be set manually to determine what should be penalized more, but after that, it is a way to automate the state space representation. The policy computed by LQR is from the local model, which is not globally correct. This will result in poor real-world policy. This is because the LQR will compute policies that are very close to the distribution of the data collection from the data collection policy. That is why we introduce fitted linear models. This imposes a KL divergence constraint that allows penalization for deviation from the previous policy and cost optimization. Now that we have the background taken care of, let's dive in and take a look at the Solar algorithm. First, we will look at a quick overview of the Solar algorithm. We can see that lines 1 to 3 is the pre-training steps. Line 1, we just initialize the policy randomly, and we use it to collect data in the environment. This data is then used to train our model and learn representation of the environment. With the newly trained model and data we collected, we can infer dynamics for local models. At line 5, you use the data and the model to infer local dynamics, and then you use those local dynamics to update your policy using the LQR-FLM method we discussed. With the updated policy, we then recollect more batch data, and we can optionally retrain the model to fine-tune it. This process is done k times. Now we can look at each part separately. So this is part 1, representation in global model learning. So this is where Solar will learn representation in a global model, which will allow for a starting point for local model inferences. The objective here is to learn two posterior distributions. One over dynamics parameters, as this informs our policy update, and another over latent trajectories, since we require an estimate of the latent state as the input to the policy. Now inside the loop, we see that we have inference and latent space and the policy update. So we're going to alternate between collecting batches of data from the current policy and using this data to fit local models to improve the policy. This step utilizes the learned representation and global model to enable local model methods. The global dynamics model is used as a prior to fit local dynamics model using its posterior inference. This uses LQR-FLM control to update the policy to avoid model bias that is a common occurrence with standard LQR control. After the policy has been updated, we use it to collect new data to form a batch, and then we can optionally update our trained model with this new data. Here is a high-level overview of the Solar algorithm. The top right is the training phase. This is where the representation in global model is learned. Bottom right, this is where the local model is inferred. Bottom left, the local models are used to make policy improvements. Then using the new policy improvement, we can collect more data, which happens in the top left. We collect rollouts from the current policy. We learn representations and global models from them. We infer local models given the observed data. We update the policy, and we repeat the process. Now that we've seen how the algorithm works, let's see how it performs by looking at the experiments and results. Two of the experiments conducted were simulated environments. First was the non-holonomic car. This is the one we discussed when looking at model biases. This is when the car has to start in the bottom right corner and reach the goal in the top left. It does so by controlling its acceleration and steering velocity. To do so, it uses only 64 by 64 images as state observation. Similarly, there's the reacher environment. This has a 2 degree of freedom arm that has to reach a fixed target. It also only uses a 64 by 64 image as state observation. Additionally, 2 real-world robot tasks were conducted for experiment. They used a Sawyer robot arm. First task is to stack 2 pieces of Lego together using a 7 degree of freedom Sawyer robotic arm. When conducting this experiment, the robot only has access to 64 by 64 by 3 images as state observation with no other auxiliary information. Another task they deemed Sawyer pushing. The objective is the Sawyer robot has to push a mug along a table and get the mug on top of a white coaster. This uses only sparse binary rewards, and in this case they used human feedback. And again, it only uses 64 by 64 by 3 images as state observation. Now we'll look at the results. The non-holonomic car experiment shows that Solar and the MPC baseline are able to learn with about 1,500 episodes. PPO learns a successful policy for this task that performs better than Solar, but required 25 times more data to reach this performance. The model-based agents experience jittery results from model bias, which we can see in the graph as some variance that occurs. Now we'll look at the reacher results. We can see that Solar is outperformed by the PPO policy. However, it required 40 times more data to learn. The VAE ablation in MPC performs worse than Solar. MPC, though, has a better initial behavior because it uses the pre-trained models right away for planning. Forward prediction with MPC's learned model deteriorates quickly as the horizon increases, making long-term horizon planning impossible. MPC is unable to do these long horizon problems, but Solar does not suffer from this because it does not use the models for forward predictions. Now for the Lego stack real-world experiments, we can see that Solar is successful on all tasks, where VAE ablation is only successful on the easiest task. MPC baseline learns more quickly on the 2 easier tasks, but is limited to short horizon planning and failed on the more difficult tasks. Each block stacking task used about 2 hours of robot interaction time. By pre-training and transferring shared representation, the amount of required data can be reduced by a factor of 2. DVF is a state-of-the-art model that learns pixel space models and does not utilize representation learning. It failed to complete the 2 harder tasks even when given more data and a smaller model. These results highlight the data efficiency Solar offers by learning tasks in 2 hours opposed to days or weeks of data collection. Lastly, we'll look at the results from the Sawyer push experiment. So for this experiment, they used only sparse rewards, and Solar was able to learn in just 1 hour of interaction time. DVF performs worse with more time and a smaller model. This highlights the efficiency of Solar. If we look at the table on the right, we can see that the final distance to the goal is almost twice as high for DVF with a large standard deviation, where solar is both more accurate and consistent. So in conclusion, solar demonstrates that it's efficiently able to learn complex real-world tasks only from raw, high-dimensional image observations. It currently outperforms similar model-based algorithms and is significantly more data efficient compared to model-free reinforcement learning methods, especially when transferring previously learned representations and models. I would like to take this time to thank everyone for watching this presentation. And if you had any questions, feel free to reach out or let me know in our discussion. Thank you.